In this lecture, we will introduce the concept of a system being controllable, a very intuitive definition, and then we will talk about an important, useful test for checking the controllability of a system, namely the PBH test, or sometimes called the eigenvector test for controllability. So let's begin by defining what we mean by a reachable and a controllable system, and we're going to start talking about the LTI case where both definitions are the same. Okay, they're identical, but the general definitions are as follows, and by general I mean definitions that are applicable to the linear time varying case. So here is how we define a reachable system. So suppose we're given two time instance t1 and t0, then the system x that equals atx plus btu. Okay, so where the matrices A and B are allowed to be time varying, and the order of the system, suppose, is n. Okay, and since this system is represented by the pair of matrices A and B, sometimes instead of the system is controllable, we say the pair AB is controllable. So they mean the same thing. Okay, so or the pair AB is said to be reachable on the interval t0 to t1 if within that interval you can transfer any state from the origin, you can state the state starting from the origin to any final destination at the end of the interval, okay, at t equals t1. So that means basically if the reachable subspace is the entire space. Since this is the system is of order n, so we're talking about the case that reachable subspace equals Rn. Okay, if this is satisfied, then we say the system x that equals ax plus b, or the pair AB is reachable, okay, on the interval t0 t1. Okay. In other words, if the origin or the state at the origin can be transferred to any point in Rn. Okay, and now let's introduce the sister definition, okay, for a controllable system. Controllable system. The system x that equals atx plus btu, or the pair AB, is said to be controllable on the interval t0 t1 if any state can be transferred to, or any initial condition at t equals t0 can be transferred to the origin at the end of the interval at t equals t1. If the controllable subspace is the entire space, okay, equals Rn. In other words, if every state can be transferred to the origin. Okay, very intuitive definitions. Now we're going to see what those definitions imply for the LTI case, and then how the property controllability, equivalently reachability, their equivalent for the LTI case, can be checked. Okay, so now we will be concentrating on the LTI case, where the matrices A and B are constant matrices. Okay, so here is our LTI system, x that equals AX plus BU. Okay, system 1. And the order of the system is n. Now, we have, in our previous lecture, established the following. For an LTI system, reachable subspace and controllable subspace are identical. They're same subsets of Rn, and they are equal to the range space of the controllability matrix. And now we have introduced these definitions, reachability and controllability, which says that if the controllable subspace is Rn, or the reachable subspace is Rn, then the system is controllable or reachable respectively. Okay. So that therefore will immediately give us a simple check through the controllability matrix. Okay, if the range space of the controllability matrix is Rn, okay, or equivalently, if the rank of that matrix is n, then our system is controllable. Since reachable and controllable, they mean the same thing for an LTI system, we usually use the word controllable, okay? Instead of we drop the term reachable and use only controllable. Okay, so let's put that down. We previously established that the range space of the controllability matrix C is equal to the reachable subspace for any interval t0, t1, provided that this is an interval of non-zero length, that is t1 is strictly larger than t0, and that equals the controllable subspace, okay, for any time instance t1, t0, where C, the controllability matrix, was constructed as follows. The first k columns are the columns of B, the next k columns are the columns of the matrix A and B, and so on. You go up to the n minus first power of A. Okay, this matrix we call the controllability matrix, is the controllability matrix. Okay, now let's combine this result with these definitions. Okay, note that the system 1 is controllable, then and only then, so that's by definition. The controllable subspace is the entire space, okay, Rn. Now, this is the definition, okay. System 1 is controllable if controllable subspace is Rn, and controllable subspace is Rn if and only if the range space of C is Rn, because range space of the controllable matrix and controllable subspace we have shown to be equal, so we can say that range space of C is Rn. And that implies, since C has n rows, so that means this is equivalent to that rank of the controllable matrix is n. Okay, so that's therefore equivalent to the rank of C equals n. Okay. For a scalar input case, that can be also written as if the determinant of C, in that case, C matrix becomes square, and then we can also use determinant as part of our check. If the determinant of C, okay, for a scalar input, it's only meaningful for a scalar input. If the determinant of C is different than 0, then the system is controllable. Okay, so we have proven, therefore, our first controllability test, which is in terms of the controllability matrix. So it's now clear why we're calling it the controllability matrix. So this is our first theorem, or first controllability check. The LTI system 1, or the pair AB equivalently, or the pair AB is controllable if and only if the rank of the controllability matrix is n. If and only if the rank of the controllability matrix is n, where n is the order of the system. Okay. Now, here is another controllability test, which is, in my opinion, much more useful than, it has a wider range of applicability than this first test, okay, through the controllability matrix. Now, here's another controllability test. It's called the PBH test sometimes, and PBH stands for the name of the abbreviation, the first letters of the names of 3 scientists that established that test. So Popov, Belevich, and Hutus. Okay, PBH test. Okay, sometimes called eigenvector test. We're going to see why it's called eigenvector test soon enough. Okay, so this test says that given a system or a pair, it's controllable if and only if the following rank condition is satisfied. So the pair AB, and let A is n by n, and B is an n by k matrix. The pair AB, or the system x that equals AX plus BU, is controllable, okay, if and only if the rank of this matrix A minus lambda I, okay, so this is the first n columns come from this matrix A minus lambda I, and the remaining k columns are the columns of B. Okay, so this is an n by n plus k matrix. Okay, equals n for all complex numbers lambda. Okay, so let's call this test or condition 1. And now we're going to prove it. partly using our previous theorem. That is, we're going to use the link between controllability matrix and controllability of the system to establish the claim of our last theorem, PBH test. Okay. Here goes a demonstration, which has some useful tools that we will use later on for proving other theorems as well. From the previous theorem, okay, we know that controllability is equivalent to the rank condition to be satisfied by the controllability matrix. Okay, controllability is equivalent to, or can be checked by, the following test: B, A, B, A, n minus 1, B equals n. Okay, n is the order of our system. So let's call this test 2 or condition 2. Now this is, if this holds, then the system is controllable. And now the statement of theorem says that the theorem claims that if 1 holds, then the system is controllable. Therefore, if we show that the condition 1 and condition 2 are equivalent, then we will have demonstrated the claim of the theorem. Okay. So therefore, we will show the equivalence between the conditions 1 and 2. Okay. So 1 implies 2, and then we'll show 2 implies 1. Therefore, they're equivalent. Okay. So naturally, we divide the proof into 2 pieces. In the first part, we're going to show 1 implies the other. In the second part, we show the reverse direction. Okay, so part 1 is where we show 2 implies 1. Okay, if, therefore, this condition in terms of the controllability matrix is satisfied, then 1 must hold. So that's a little bit easier than showing the reverse direction. So let's start with the easy piece. So what we're going to do is we're going to try to show this by contradiction. Namely, we will assume that 2 holds, but 1 doesn't. Okay, and then we're going to proceed from that premises, and we will reach a contradiction, which will tell us that whenever 2 holds, 1 must also hold. Okay. Okay, suppose not. That is, 2 holds while test 1 doesn't, condition 1 doesn't. Okay, so A minus lambda I B, this matrix, which is an n by n plus k matrix, has n rows. Okay. So, and we're assuming that 1 doesn't hold, so that means those n rows must be linearly dependent. Okay, so that means the rank is less than, strictly less than n, if 1 doesn't hold. So this guy has n rows. Hence, if the rank condition is not satisfied, rank of A minus lambda I B is less than n for some scalar lambda, then the rows must be for that particular lambda, the rows must be linearly dependent. The rows of this matrix for that particular lambda must be linearly dependent. Okay? Which is equivalent to that the columns of the transposed matrix must be linearly dependent, because the rows of this matrix the same as the columns of its transpose. So we will work with the transposed matrix. It's a little bit easier. Columns of A transpose minus lambda I transpose, but I is the identity matrix, therefore its transpose is itself. And here we have B transpose. Now this is an m plus k by n matrix, meaning that it has n columns. And now we start with the initial condition that the condition 1 doesn't hold. Therefore, those n columns for that for some particular lambda are linearly dependent. Okay, must be linearly dependent. Okay, and that implies that we can find a linear combination of those n columns where at least one of the coefficients are different than 0, such that their linear combination produces the 0 vector. In other words, we can find a non-zero vector V, okay, in Cn, such that A transpose minus lambda I B transpose times that vector V produces 0. Okay. Now let's figure out the implications of this equality. So that implies that this times V equals 0, and that can be written as A transpose V equals lambda V. Okay, now that this becomes the eigenvector equation, eigenvalue, eigenvector equation, where V, since it's non-zero, V appears as the eigenvector of the matrix A transpose. Furthermore, B transpose times V equals 0. That means this vector belongs to the null space of B transpose. Okay, so this is interpreted as V is an eigenvector of the matrix A transpose, and this is interpreted as V belongs to the null space of B transpose. Okay, now we're going to make use of these two observations and immediately obtain that if those two things hold, then the rank of the controllability matrix cannot be n. So let's see how that goes. Now, we proceed as follows. Observe that C transpose V equals what? And by C we mean the controllability matrix. Okay. Now C transpose V equals, what's C transpose? Is B transpose. Then we have B transpose, A transpose, and finally we have A n minus 1 transpose, and that's multiplied by the vector V. Okay, so that equals B transpose V, B transpose A transpose V, and so on. Okay. Okay, and that equals what? This is B transpose V, and A transpose V is lambda v, and lambda is a scalar, therefore we can put it anywhere we like. So let's put it here, lambda times B transpose V, and then we have B transpose A transpose square times V. Now, since V is the eigenvector of A transpose, naturally it's also the eigenvector of A transpose square, or any power of A transpose, and the corresponding eigenvalue will be lambda raised to the appropriate power. Okay, so here for the third row we will have lambda squared B transpose V, for the fourth row we have lambda cube B transpose V, and so on. And for the last row, nth row, we have lambda raised to the power n minus 1 times B transpose V. Okay, which we were able to write because V is not an arbitrary vector from the point of view of A transpose, but it's an eigenvector of V. And then V also belongs to the null space of B transpose, therefore this is 0, and everything is 0 multiplied by lambda to the power something, but it will not change anything, and everything becomes 0. Now, what we have obtained is the following: C transpose times a non-zero vector V produced 0. So that means the columns of C transpose must be linearly dependent. How many columns C transpose has? It has n columns, okay? Therefore, the columns of C transpose are linearly dependent. Rows of C equivalently are linearly dependent. And it has n rows, C has n rows. Therefore, the rank cannot be full. Okay, rank must be strictly less than n. Hence, if one doesn't hold, then 2 cannot hold either. And that would produce a contradiction. Okay. So, rank C cannot be n, and the result follows by contradiction, meaning that whenever 2 holds, so must 1. Okay, now let's show the more subtle piece, namely the part 2, where we will show that 1 implies 2. Okay, second part. 1 implies 2. Okay, again, we're going to use contradiction. That is, we will suppose that 1 holds, but 2 doesn't. And then we're going to reach a contradiction. Or in other words, what we're showing is not 2 implies not 1. Okay, so which is equivalent to, from the logic point of view, that claim 1 implies 2. So suppose not, okay? That is, 1 holds, but 2 doesn't. Now, 2 doesn't hold means that the rank of the controllability matrix is strictly less than n, okay? So rank of controllability matrix C is strictly less than n, okay? Or not equal to n, since the most the rank can get is n. So that means we can find, so if the rank is strictly less than n, so that means the rows of the C matrix must be linearly dependent because C has n rows, or equivalently, columns of the C transpose must be linearly dependent. Okay? So that implies, therefore, that there exists a non-zero vector V such that C transpose V equals 0. Okay? So this simply means that the columns of C transpose must be linearly dependent, which is equivalent to saying that rank of C is not n. Now remember C transpose, actually it's here, this is our C transpose, okay, B transpose, A transpose, and so on. So C transpose times V equals 0 can be written as the following n equations. B transpose V equals 0, B transpose A transpose V equals 0, and so on. B transpose A n minus 1 transpose V equals 0. Okay, now by looking at these n equations, what we're going to do is, first we're going to define the following subspace of Rn. Okay, define the following subspace, span of the following vectors: V, A transpose V, A squared transpose V, and so on, up to A n minus 1 transpose V. Okay, so that is a subspace of Rn. Okay. Now let's make the following observations. Observe that this subspace must be a subset of the following null space of B transpose. Why is that? Because B transpose times V is 0, B transpose times this vector is 0, B transpose times the next vector is 0. So B transpose times any vector from this set is 0. So clearly B transpose times any linear combination of these n vectors must also be 0. Since linear combination of these n vectors, all the possible linear combinations, produces, by definition of span, produces this subspace S. This subspace therefore necessarily is a subset of the null space of B transpose. Furthermore, by Cayley-Hamilton theorem, you take any linear combination of these n vectors, multiply by A transpose, and since everything is some power of A transpose times V, each of those entries, that linear combination multiplied by A transpose must also be a power, can be written as a linear combination of powers of A transpose. Okay? And by Cayley-Hamilton theorem, you don't have to go further than the power n minus 1. Therefore, automatically, take any vector from this subset, multiply by A transpose. Again, it must belong to this subspace. In other words, that subspace S is invariant under the matrix A transpose. S is invariant under A transpose, okay? Which once again means that take any vector from S, operate on it with A transpose, okay? A transpose times X, you obtain a new vector, and that new vector, by Cayley-Hamilton theorem, must also belong to this subspace. By Cayley-Hamilton theorem. Okay, now from this point we proceed as follows. What we're going to do is we're going to now pick or construct a matrix whose columns make a basis for our subspace S. And then using the invariance, we will eventually construct an eigenvector of A transpose satisfying some properties which will give us that if 2 doesn't hold, then 1 cannot hold either. So let's see how that goes. Let now capital V, okay, capital V, which is an n by L matrix, and L is the dimension of the subspace S. Okay, n by L be a matrix whose columns make a basis for S. Okay, so by definition, because we're using the word basis, by definition, those vectors or those columns are linearly independent. Okay. For S. Since the subspace S is invariant under multiplication by A transpose, we can find a square matrix lambda, okay, L by L. L is, once again, the dimension of our subspace S, such that A transpose V equals V times lambda. Okay, now let's interpret this equation, or try to see what it says. Now, take the first column of V, A transpose times V, okay? Since the first column belongs to S clearly, because all the columns span S, A transpose times the first column is in S. So that means it can be written as a linear combination of the basis vectors, namely the columns of V. Now, write that linear combination, and each vector will be multiplied by some coefficient. Collect those coefficients and make a vector of size L, and that vector makes the first column of this matrix lambda. Go to the second column of V, A transpose times that second column is a member of S, therefore it can be written as a linear combination of the columns of V. Write it as a linear combination, collect the coefficients, make a vector of size L, and that vector is your second column of lambda, and go in this fashion to obtain the matrix L by L square matrix lambda. Okay, so let's call this equation 3. And now, since lambda is a square matrix, it will have at least one eigenvector. And let W be that eigenvector. L be an eigenvector of the square matrix lambda. That is lambda times W equals alpha times W for some alpha. Okay, which would make the eigenvalue corresponding to that eigenvector. Eigenvalue of what? Eigenvalue of this matrix lambda. Now, let's multiply both sides of equation 3 with this special vector W, which is an eigenvector of lambda. Okay, so then we proceed as follows. 3 implies A transpose V lambda equals V, times W equals V times lambda times W. Okay, what we did, we took equation 3 and multiplied both sides by the eigenvector W. Okay, that equals what? Lambda times W is alpha W. V times alpha W. Alpha is a scalar, therefore we can put it anywhere we like. That produces alpha times V times W. Now V is an n by L matrix. W is a vector of size L. Therefore V times W is a vector of size n. Okay. So what we have obtained therefore is, so let's call that vector Z. Okay, Z V times W, which is a vector in Cn, is an eigenvector of the matrix A transpose. Okay, why is that? Because here we have A transpose times Z equals alpha times Z. And this Z, this vector, in order for it to be eigenvector, it should be non-zero. Is it non-zero? Yes, it is, because V has linearly independent columns and W is a non-zero vector, so clearly that product can never be a zero vector. Therefore Z is a non-zero vector and it satisfies A transpose times Z equals some scalar times Z. Clearly Z is an eigenvector of A transpose. Furthermore, Z belongs to the subspace S. Why is that? Because Z we can write as a linear combination of columns of V, and the columns of V span the subspace S. Therefore, Z must belong to that subspace S. Okay, subspace S is here. Okay. And since Z belongs to subspace S, and subspace S is a subset of the null space of B transpose, automatically Z must belong to the null space of B transpose. Z belongs to the null space of B transpose, or in other words, B transpose times Z must be 0. Now, all that remains is to put all pieces together. Okay, so finally we have the following: A transpose minus alpha times the identity matrix, and put here B transpose. Okay, now this matrix, which is n plus k by n plus k by n times the matrix Z equals A transpose minus alpha identity times Z, and here we have B transpose Z. Okay, and that equals 0 for the first entry, because Z is an eigenvector of A transpose with corresponding eigenvalue alpha. Okay, it's here. And the second entry is 0 also, because Z belongs to the null space of B transpose. So what we have obtained is this matrix times a non-zero vector Z equals 0. So that means this matrix here must have linearly dependent columns. Okay. Hence its rank cannot be n, because it has n columns. Clearly the rank of its transpose cannot be n, because rank of a matrix and its transpose, they're always equal. So that implies rank of its transpose cannot be n. Okay. So what we have obtained is the following: if the controllable matrix is of rank strictly smaller than n, if its rank is not n, then the rank of this matrix for a special alpha, for at least one alpha, is also not n. Okay, and that gives us the contradiction that we want, which completes part 2. Together with it completes, and as a result, it completes the entire proof of our theorem. Okay, so let me finish with this remark. We can restate the claim of the theorem that we have just proved, or we can restate the PBH test as follows. Okay. Now, once again, what's PBH test? What we have proven? We have proven the following: a system is controllable if and only if this matrix, okay, has rank n for all scalars alpha. Okay. And since Okay, this matrix having rank n is same as this matrix having rank n, and this matrix having rank n means that there is no z that satisfies this. When you multiply by z, you obtain 0, and that z, if you have such a z, that z would be an eigenvector of A transpose, that's the null space of B transpose. We can restate the PBH test as follows. System x that equals ax plus bu is controllable if and only if no eigenvector of A transpose belongs to the null space of B transpose. There is no eigenvector of A transpose that belongs to null space of B transpose. Okay. For this reason, PBH test is sometimes also called the eigenvector test for controllability. Okay.